Hi, so this is part two of my Sitcom NLP script data project. In the first part, I went over notebooks 1 and 2, which were about obtaining and cleaning our data, and then also performing exploratory data analysis on the data. So if you want a little bit of background on what we're about to explore some modeling techniques on, then go ahead and watch part one. Um, as for part two, let's dive right in. I decided to start with just some basic classification techniques using TF-IDF. Um, so after I imported these libraries over here, um, I began with a little bit of text data preprocessing. If you look in my Jupyter notebooks, then you'll see that I did do a lot of these steps already at a couple different parts in notebook 1 and 2, while generating my LDA topic model or when I was exploding the rows in while creating the initial data frame. But I thought that it would be worth it just to go over some of these steps and create a little bit of a checklist. So of course, pretty standard stuff, just converting the scripts to lowercase, removing punctuation, removing stop words. I also did take a look at some of the top 10 common words in these scripts, and I decided they weren't super formative, so I decided to take those out as well. And then I used NLTK's tokenize function to tokenize the data. And so then I decided to use term frequency inverse document frequency to vectorize this data, which there's a little overview here if you would like. The first thing I did though was I created a variable for total vocabulary. As you can see, it looks like we've got about almost 11,000 unique words in the total vocabulary, so that's pretty cool. And then I used, after I added each line of the script into a list, I took a look at the frequency distributions of each word. So this isn't super informative just because, it's not split up by class. We don't know which words were more common in failed versus successful sitcoms. But I did notice a couple interesting things, such as the fact that I thought it was kind of funny that guys was right above people, since I sort of use those terms a little bit interchangeably, I guess not completely, like hey you guys, let's go, versus hey you people, let's go. It is a sitcom that we're talking about. And I also thought that it was kind of funny that the word dad was above mom, because I find that I use the word mom a lot more. But like I said, this wasn't super informative, just kind of interesting to look at. You can't really draw too many conclusions from it though. So I moved on to TF-IDF vectorization here. As you can see, our vectorized data has about 21,000 vectorized articles, um, and 8,771 unique words. So let's see. I decided to then run about 6 classifiers on the data: multinomial naive Bayes, random forest, logistic regression, decision tree, k-nearest neighbors, and support vector machine, which I initialized up here and then ran over here. They all ran pretty quickly, which was nice. And then looking at our performance, I did also print out the training scores. Remember, we don't have a lot of data. We only have about 28,000 lines or rows in this data. So I think that is kind of, that was a drawback, because as you can see, there's a lot of overfitting. As you can see, some of these training accuracy scores did get pretty high. We have 92 for both random forest and decision tree. And even like logistic regression, we got some 75s here. But as you can see, these numbers fell a lot on the test set, which of course is a fraction of our data overall. Our highest testing accuracy was about 62% with multinomial naive Bayes, so that's not great, but these training scores do give me hope. So like I said, I do think that it is because of our small sample size, but there's still, we should see if we can fix some of these overfitting issues. So I decided to run a latent semantic analysis on our data to perform some dimensionality reduction. It's kind of like, I think like the text version or text variable version of PCA, Principal Component Analysis. We used sklearn's truncated SVD function to perform this dimensionality reduction. So this reduced computational load and also improved the type of features that we kept. We ended up only running 5 of these classifiers. We actually dropped multinomial naive Bayes since it doesn't run on negative values. If we wanted to run a multinomial naive Bayes, we could have used a non-negative matrix factorization instead of SVD, but I wanted to start an experiment with SVD for the purposes of this project. So let's look at this performance. As you can see, our testing accuracy is not good. It all hovers around 50% with a high of 52%. It looks like, obviously that's roughly the naive, or that is the naive guessing rate because we do have a binary. The training accuracy, these scores look pretty similar to the ones above, although they're slightly lower. So obviously TF-IDF worked a little better without the LSA. Now I wanted to take a look at how our TF-IDF data performed with the features that we generated, which we generated at the end of our EDA notebook, which is notebook 2. Just as a refresher, a couple of those features that we generated were things like number of characters in a line, or the amount of profanity in a line, parts of speech. We had about 15 features that we generated. So first thing I did here was I used standard scalar to normalize these numerical columns of our new features. And then I actually went ahead and used a function I hadn't used before, which is SciPy HStack, which is used to horizontally combine sparse matrices without having to convert anything to a dense format. Check our shape. As you can see, this number over here is increased by about 15 to account for the 15 new features that we added. And then I ran our classifiers with the exception of, again, multinomial naive Bayes because of the negative numbers thing, and also I omitted a support vector machine because it took a long time to run and it wasn't performing very well on our other data anyway. And I was impatient at this point in the project. So looking at these scores, better than our LSA scores, but not great. Looks like the training scores are pretty similar to what they were with our TF-IDF alone data. Meanwhile, our test scores, again, still just not performing any better than they were on our first run through. But so I guess that this kind of meant that our new features weren't doing well with the TF-IDF data. I did want to just see how they performed on their own, just for peace of mind. So over here, kind of repeating this process, but only using our feature data this time, not the TF-IDF data. And looking at this performance, we have our lowest training score accuracies yet, with 80% on, our top dogs, random forest and decision tree, and our testing accuracy is again pretty much just 50% across the board. I did go ahead, though, and for convenience, compile this all these scores of the models into one data frame. First thing I did was I sorted it by test scores. As you can see, again, actually the first classifier we ran, multinomial naive Bayes on the TF-IDF data, was our lead with the 62.5%. But as you can see, like the top 10 models, or all 6 instances of our TF-IDF modeling occur in the top 10 of our 19 total models that we ran, and the top 5 models all have 3 of them are TF-IDF data, with the other 2 being on the combo data. At the bottom here, we've got our feature set, specifically random forest with about 50.3 or 50.4%. But that's not saying much because, as you can see, I think about 7 of our models had about literally 50%. I guess some of these round up a little higher, but And then I did, just for fun, also sorted by the train scores as well. Up here, it looks like random forest and decision tree are pretty much tied. Their numbers are really similar, if not the exact same, for most of these data models, and they make up pretty much all the top classifiers Support vector machine, which we stopped using by our third run through, is at the bottom with not so impressive scores. So we did have a pretty big range though, you know, a lot in the 50s, but also some in the 60s, 70s, 80s, and 90s. So again, I think that a lot of, you know, our problems here are because of our small data size, but let's go ahead and take a look at some of this deep learning. So with this, we actually did pretty much dive right in, actually. You know, we just set our target variable real quick, and then we did do a little bit of pre-processing using Keris's pre-processing library so that it would work optimally for our Keris model that we were going to build. We used Keris tokenizer, limiting our vocab to about 20,000 words, and then we used the text-to-sequences function to convert our lines to sequences, and then finally we padded the sequences so that they would all be the same length. Move on to our test train split, and then we went on to building our neural network. We did make an LSTEM recurrent neural network here. The first layer is an input layer, followed by an embedding layer, which is where we defined how large the word vectors would be. Up here we have embedding size equals 128. And we also use this time to specify the size of the embedding space itself, which we put as 20,000 because that's what we limit our vocabulary to during the tokenization process. So from there we've got our LSTEM layer, and then a pooling layer, a dense layer, and then finally our output layer with a couple dropout layers in between to reduce overfitting, which of course is one of our big problems. Here we have a little visual of our model. And then we moved on to fitting and compiling the data. Since it is just two classes, we used a loss function of binary cross entropy. And then we also used, for our optimizer, we used Atom, which is a gradient descent, an extension to gradient descent that's become pretty popular for NLP projects recently. And then we fit our data. We used 50 epochs again, just again for sake of time. And then we printed out the scores. So over here we've got a test accuracy of about 61%, which is not great. But you know, if we do look at the output above, we did see that the accuracy did get pretty high on some of these runs. And our test loss was about 1.67. So I did take care to produce a couple graphs. As you can see, these visuals also show the gargantuan difference between the performance of our training set and our validation set, which I forgot. We did specify a validation set up while compiling the model because Keris does work best when you have test train validation split. But after seeing this performance, I did kind of go back to my notes, and I realized that when you have a small sample size, people tend, or k-fold cross-validation seems to be the better way to use cross-evaluation so that you don't have to give up any more of your data. So over here we just defined a quick k-folds function with some output, and then we reevaluated the original model that we made. So over here you can see that this did perform a lot better. Our mean validation accuracy score was actually 80%, which is awesome, with a standard deviation that was pretty low. And then we've got a couple graphs for our loss function, which do look different from the graph above. Overall, this took about 30 minutes to run, which is definitely worth it for a 20% increase in accuracy, as well as our average loss function went from being 1.9 to about 0.35, so that's great. And then finally, though, I just wanted to try something new, so I did try using a pre-trained glove data, which I've got a link for here. So the first thing I did though was, you know, this pre-trained glove data had vectors for 6 billion words, but since our scripts aren't that sophisticated, I once again made a total vocabulary variable. This one looks a little bit different than it did in our classification notebook because we didn't go through all those pre-processing steps, because again I wanted to try something a little bit different. Over here we're just opening glove and reading the vectors. Here I plugged in the word hello just to see how it worked, and as you can see, it did. And And then I moved on to quickly just defining a couple variables in here, and then finally creating an embedding matrix. So one of the big differences here is I did make a variable for the length of our longest sentence, which is also how we ended up padding our sentences later over here when we reran these pre-processing steps, again, so that I could pad the sequences or sentences to be the same length. Test train split again. In this model, we made it a lot more simple. We didn't include an LSTEM layer. We just have the embedding layer. Over here again, we have a little visual of this. I compiled it with the same optimizer loss and metrics, and then again ran it with 50 epochs. We didn't use the k-fold cross-validation, again for the sake of time. And as you can see, that reflects in our scores. We get a test loss of about 0.76 and test accuracy of about 0.54 or 55. So 55% is not a good score for binary classification. But again, I do think that part of that is just because we didn't use the LSTEM layer or use a k-fold cross-validation, sorry. So, my biggest conclusions from this were, mainly that to really assess the validity of this project, we would have to, I think, just gather more data. There are things in the future that we could do with the data at hand. For instance, I had a lot of descriptor columns in the original data frame that I created. So it'd be pretty interesting, I think, to run EDA on some of those other variables, like even the actors variable. Additionally, there's more feature engineering we could do. We could also do more, hyperparameter tuning up here. We didn't really do any of that in the classification or deep learning notebook. We could have tried out PCA for our original extra feature set. But so far, I think that we did a pretty good job with what we had, and getting our test accuracy up to 80% on average with our Keras LSTEM model created with the original word embeddings. That obviously that's pretty good. Not as good as the 95% or roughly 95% accuracy that we got on the training data with some of these classifiers like random forest and decision tree on the TF-IDF data, but definitely not bad, and I think this is definitely a good starting point. And there's a lot of ways that we could have increased this data size. As I said, I had trouble accessing scripts for shows that were made, or failed shows made before 2009. But again, with more time, money, resources, I feel that we could definitely gather some additional data, as well as maybe opening up the criteria to include shows made by HBO or Netflix, or maybe widening the time frame of these shows, such as taking shows created before 1989 as well, so we can include things like I Love Lucy or Cheers. But anyway, that is my Flatiron Capstone project. Thank you for tuning in, and see you soon.